All right, guys. So we'll move on to the last exercise of this particular lesson. Okay, so exercise 4E. Okay, so let's see how we can go into some more deeper questions with respect to vertical circular motion. Okay. Okay, so they say wherever numerical value of G is required, take G as 9.8. Okay. So a particle P of mass m is attached to one end of a light inextensible string of length L. The other end of the string is attached to a fixed point O. The particle is hanging in equilibrium at a point A directly below O. Okay, so guys, you picture this, right? So the particle is at the beginning, it's hanging directly. Okay, so when it is set in, okay, so the particle is hanging in equilibrium at a point A directly below O when it is set in motion with a horizontal speed root 3 GL. Okay, so when OP has turned to an angle theta and the string is still taut, the tension in the string is capital T. Find an expression for capital T. All right, so let's draw a diagram. All right, so you have this particle, it's directly hanging. So this is the fixed point O. And this is the point A. All right, so this is how the particle moves, right? The circular motion part. All right, so this is the circular part. What you need to do here is when OP has turned to an angle theta, so take another point. So take another point on this circular part. Okay, so when OP has turned to an angle theta, so this is the angle theta. Okay, the string is still taut and the tension in the string is T. Okay, so we'll mark the tension here as T. You have the weight mg. All right, so you have the weight mg. The tension string is T. Okay, find an expression for T. All right, so let's find it. Okay, let's mark the speeds as well. So they say here the particle is hanging in equilibrium when it is set in motion with a horizontal speed root 3 GL. All right, so at the starting point, the speed is root 3 GL. So over here at this point, the speed, let's mark it as V because we do not know the speed. At that point, at the general point, the speed is V. Okay, so to find an expression for T, we had to do the same thing which we did in the previous exercises. Okay, so in the previous exercise, we learned the concept. We learned how to the base concept of vertical horizontal motion, right? So you always apply conservation of energy and you apply F equal ma towards the center. So those are the two main rules that you have to do here. All right, so I will set the lowest point as the GP0 level. Okay, so or you don't need to actually set the GP0 level if you go with the law of, I mean, if you could go with the potential energy gain, kinetic energy loss, you would go with that as well. Okay. Okay, so let's apply the law of conservation of energy. All right, so by the law of conservation of energy, so initially we have kinetic energy, right? Kinetic energy initial. Okay, so at the initial point, it's at the lowest, so there's no GPE. At the final point, you have kinetic energy, the final amount. So it's definitely lower, right? Because you understand when you're moving up, the speed decreases. It should be a lower KE. And then at this point, you should have GPE or potential energy. Potential energy, final, or basically it's the gain in GPE. So if you subtract KE initial with KE final, you get the kinetic energy gain and the kinetic energy loss actually, right? So because it's losing speed, KE initial, if you subtract with KE final in one side, that gives you the KE loss. Equals on the other side, you have the potential energy gain. Okay, so you can go with that or you can just substitute with this. Let's go with this half mv square. So half m, the speed here is root 3 GL, and you should square that. Kinetic energy final half mv square plus GPE. So GPE is mgh. What is the height? So guys, what's the height here? So you'll have to get the height here. So how do we get the height, by the way? So do we have the radius? Have they told us what the radius of this thing is? A particle P of mass m is attached to one end of a light inextensible string of length L. Okay, so the length of the string is L. Can you guys see? So this is a string of length L. Okay, so then this length is going to be L towards the angle L cos theta. Can you guys see? So this particular length is L cos theta. So then you can see the height difference that I require, the h that we require is going to be L minus L cos theta. So you see this whole length is L, and when you subtract L cos theta, you get the length that you require. I mean, we require this height, so that is this red color height is from L, you subtract the L cos theta. All right. All right, guys. So now let's simplify. So you can cancel out m. Everyone has m. You cancel it out. So you get here half into root 3 GL square. It's going to be 3 over 2 GL, right? So 3 over 2 GL equals half V square. Over here you have GL minus GL cos theta. Great. Let's multiply the whole equation by 2 because I have half V square and I'm trying to make V the subject. All right, so my goal here is to make V the subject. So you get here 3GL V square plus 2GL minus 2GL cos theta. So if I make V square the subject, you guys can see it's going to be 3GL minus 2GL is 1GL plus 2GL cos theta. Okay. All right, so we have this equation. So this is the V square equation. All right, so now we're supposed to find the tension. So we'll now apply F equal MA towards center at the general point. Okay, so what do we have? F equal MA towards the center. So you require to definitely resolve the forces. So as you can see here, you can get the theta angle over here. So this theta angle over here, you can take it out here as well, right? Guys, this angle over here is theta as well because of corresponding angles. Can you see? So you need to be good with your geometry here. So this theta comes over here, corresponding angle. Okay, so now you can go for the resolving of mg because I need the forces who are acting towards the center or away from the center. So you can see if I resolve mg, I get here mg cos theta because you are resolving mg towards the angle. Can you see mg towards the angle? You get the mg cos theta, the mg cos theta force. Mg sin theta, the other side we do not require that. Right, so we are only concerned about forces who are acting in the towards the center direction or away from the center direction. All right, so let's apply F equal MA. So we get here towards the center tension, mg cos theta x away from the center. Okay, so T minus mg cos theta equals, that's all right. Those are the only two forces we are concerned here. So equals mass into centripetal acceleration v square over r. Agreed? All right, so let's get the expression for the tension. P minus mg cos theta m over the radius is, guys, you know the radius. Now I told you be careful, replace the radius value. So over here the radius is L. Okay, and v square value we just found. V square value was GL plus 2GL cos theta. All right. So I get here T minus mg cos theta equals m over L into GL is mg plus 2mg, L and L cancels, cos theta. Guys, can you see? And the bracket L cancels out. So now make P the subject. P equals mg. So you have here 2mg cos theta plus another mg cos theta. That gives you 3mg cos theta. So to make things look better, you can maybe take mg out and write mg plus 3 cos theta newtons. So this is the expression for the tension. Okay, so guys, now we'll move on to part B, and this is where things get a little bit, where you need to think a little bit extra. Okay, so part A, applying conservation of energy and F equal ma towards the center. I think we've practiced this with many sums in the previous exercise, right? So this was what we did before, but now let's go to the next part. So where we are going to go into the next level of the circular motion, basically things that could happen while the particle is moving in the circular path. Okay, so look at this. Now they say here, part B, find the height of P above A at the instant when the string goes slack. So guys, what are they trying to tell here? So over here now you can see when you give the root 3GL, the particle is moving, right? So the particle is moving in this particular path. What I want you to understand here is, you guys need to realize now if the string is becoming slack, the first thing I want you to understand is during this part of the motion. So let me highlight it. So this part, can you see this green color part? So while the object is moving in this part of the motion, do you think there is a chance that the string could actually become slack while the particle is traveling in this part? Okay, so now at this point, we are not talking about, you need to understand, we are not talking about circular, kind of circular motion that has complete vertical circles. Okay, so we are not talking about it. So we are talking about circular motions that reach a certain limit. All right, so it doesn't go to the very top. So over here, what I first want you to realize is at this section, okay, so 90 degrees, I mean below the horizontal, basically. Do you think there's a chance that the string could actually ever become slack at this particular part? All right, I think you guys can understand with your common sense and even with considering like the motion of the simple pendulum also, you can see when you are in that downward section, these downward sections, you need to understand anywhere in this downward section, okay, below the horizontal, there's no way the string becomes slack ever because the weight is acting downward. So the string is always being pulled. So there's no reason for the string to become slack below the horizontal. So that's the first important thing you need to understand. Okay, so then if the string becomes slack, you need to understand it will become slack after it passes the horizontal, meaning when it goes up over here. So anywhere over in these kinds of paths, anywhere over here, yes, the string has the potential. I mean, it could go, the string could go slack because the weight is acting down, the tension is acting over here. So there is a good, the string could go slack. All right, so that's what I wanted to understand. Anyway, so over here they are saying you're supposed to find the height of P above A at the instant when the string goes slack. All right, so let's do it like this. Part B. So when the string goes slack, what happens? The tension in the string reaches 0. The tension in your string becomes 0. So all right, let's write T equals mg plus 3mg cos theta, right? P equals mg plus 3mg cos theta. The expression, the one we got before the last. Mg plus 3mg cos theta, right? So when the string goes slack, tension becomes 0. mg plus 3mg cos theta, and you get here minus mg equals to 3mg cos theta. Mg cancels out and you get cos theta equals to minus 1 over 3. Can you guys see this? Cos theta equals minus 1 over 3. And if you type cos inverse minus 1 over 3 in your calculator, you will see you get a what kind of an angle? Cos inverse minus 1 over 3 is an obtuse angle, isn't it? Type cos inverse minus 1 over 3. Just get your cal to the degree mode so you can see it easily. Get your cal to the degree mode and type cos inverse minus 1 over 3. And you can see that I just proved to you what I said, right? I think you can see now you measure your theta from this downward vertical, right? You measure the theta from this downward vertical. So over here, you can see the string becomes slack somewhere over here, like when you have an obtuse angle, isn't it? So when this theta angle is obtuse, can you see? Cos inverse minus 1 over 3, how much is it? Cos inverse minus 1 over 3 is 109.47, something like that, 109, yeah. So 109 is the, I mean, when you make an angle of 109 with the downward vertical, that's when the string goes flat. You guys are with me? So that is when the string goes flat. So when your theta angle, so when this becomes the theta angle, basically your theta angle is now obtuse. Agreed? All right. So the thing is this, I'm supposed to find the height. Okay, I'm supposed to find the height, but you can see now the theta angle that we are working with is an obtuse angle. So normally we resolve and we do all the things with acute angles. So you can see right now the theta angle that we are working with is an obtuse angle. So to find the height above it, they're asking to find the height above it at the instant when the string goes slack. So this is the place where the string goes slack. The tension is basically becoming 0 at this point. So you need to find this height. So guys, how are we going to find this height? How are we going to find this height? So I think you can see we can break the height into 2 sections. Okay, so the first section height is not difficult, right? So this part of the height is the radius. Can you see? It's the radius or it's the length L. Can you guys see from the center and downwards? Point A, that's the radius, the length L. But I think the other part of the height is where you'll need to improvise a little bit. So this part of the height, you'll need to get an angle. So this is the length L. Okay, so this is the length L. Okay, so how do I get this small height? How do I get this particular part of the height? Can you guys see what I'm trying to find? How do I get this green color height? Because the height that I require is the full one, the green color part, plus the length L part. Do you agree? So I need to find the green color height. So to find the green color height, it's easier if I can deal or if I can work with an acute angle. All right, so how do I get that? Okay, look, so I'm going to do a little bit of a technique here. I'm going to mark the acute angle. Now over at this point, you know, theta is the obtuse angle, right? So let me mark the acute angle with the upward horizontal. I'll mark it as alpha. Guys, are you with me? I'll mark the upward, the acute angle as alpha. Great. So we know in this case, theta is equal to 180 minus alpha. Guys, do you agree? Theta is equal to 180 minus alpha. Is that okay? That's correct, right? Okay. You can't go with arctan or anything here because you do not know these distances. Okay, so I can build up the relationship that theta equal 180 minus alpha. That's correct, right? So the obtuse angle theta is equal to 180 minus the acute angle alpha. And now what I want you to do is take the cost ratio of both the sides. So this is P2 trigonometry. So if you have two angles are equal, then the cost ratios of those angles are also equal, right? Even the sine ratios are equal. Even the tan ratios are equal. So if theta is equal to 180 minus alpha, then sine theta should be equal to sine 180 minus alpha. Tan theta should be equal to tan 180 minus alpha. Cos theta should be equal to cos 180 minus alpha. That's common sense, right? Are you with me? Okay. So now you know the value of cos theta. Cos theta is minus 1 over 3. So guys, this part is P2 trigonometry. So you need to recall P2 trigonometry. So you have done in P2 trigonometry here, alpha is acute angle. So when you have 180 minus alpha in P2 trigonometry, you dealt with quadrants, right? So this is just something that I'm doing independently. If you remember your P2 trigonometry, this is really easy because uh, when you're in 180 minus alpha, you're on the second quadrant. Angle alpha is the acute angle. Can you see 180 minus alpha? You're on the sine quadrant. So if you are taking a cost ratio from the sine quadrant, it should be negative, right? Do you recall these things? Minus, the cost doesn't change. Okay, even though you are in the sine quadrant, the cost ratio doesn't change. Just because you're taking cost ratio from the sine quadrant, you have to input a minus. And this becomes minus cos alpha. So basically, minus 1 over 3 equal minus cos alpha, which gives you cos alpha equals 1 over 3. Guys, can you see? So this is something that can help you a lot. So getting an acute angle ratio is so helpful, but you should know what you're doing. Okay, but you should know what you're doing. Okay. So get this, cos alpha is 1 over 3. So now I have the alpha value, the acute angle. So since I have the acute angle, now I can easily get, so you can see this angle alpha, which I marked over here. Guys, can you see this angle alpha, which I marked over here? Okay, now I'm coloring this in blue. I could get it to the other side by using this alpha over here comes because of alternate angles, right? Can you see? Simple geometry. So this alpha over here comes over here as well. And now you can get this small height, the green color height. How do you get the height here? It's L cos alpha. Can you guys see? It's L cos alpha. Okay, so these kinds of things, the understanding is important. So what happens here? The total height of P above A when the string goes slack. So total height when the string goes slack is equal to L plus L cos alpha. Great. So this length L plus L cos alpha is the total height the string achieves. It's going to be L plus L times cos alpha is 1 over 3. So L plus 1 over 3L, that's 4L over 3. So that's the total height the particle achieves when the string goes slack. Okay. All right, guys. So now we'll move on to the last part. Guys, I hope you understood this section. Okay. So this is something that you require to know a little bit of P2 about. Okay. So in P2, you have learned to take these kinds of ratios, not only for cos, but for sine and for tan as well. Okay. So just to give you a heads up, like, what if you take the same thing, sine 180 minus alpha, just to give you a heads up, because you guys, I think, might be having trouble with this. 180 minus alpha is in the second quadrant. Sine 180 minus alpha falls to the sine quadrant. 180 minus alpha, it goes to the second quadrant. So in the second quadrant, sine is positive and you get right the sine of the acute angle. That's how it's done. If you take tan 180 minus alpha, now this is something that's outside of what we are supposed to do, okay? Tan 180 minus alpha will give you, so in the 180 minus alpha is the second quadrant. In the second quadrant, tan falls to the sine quadrant. So therefore, it's a negative, and you should write the tan and you should write the acute angle. That's how it's done. Okay, you can even do this for 180 plus alpha, even for 360 minus alpha. So you learn this, you learn all this stuff in P2. Okay. So just recall that if you don't remember, because it's important that you are able to convert obtuse angle ratio to an acute angle ratio. Okay, so to make your life easier. All right, part C, they ask you to calculate the maximum height above A. A is the lowest point here, right? They're asking you to find the maximum height reached above A reached by P before it starts to fall to the ground. Okay, so what does that mean? Now, at this point, when the string becomes slack, okay, so what's happening? The thing is this, after the string becomes slack, so now these are really important. Okay, so this is connecting M3 to M2. Okay, so after string becomes slack, what happens? The particle starts moving as a projectile. So guys, we are in M2 now. The particle starts moving as a projectile. So this is now going to be entirely dependent on M2 projectile theory. Okay, so basically the stuff you need to know in M2. So then it doesn't go in the circular path anymore. Okay, so now you have it doesn't stick to the circular path, because all this while the particle was sticking to the circular path, but now because the string becomes slack, now the string plays no part in this. But the thing is this, when the string becomes slack, the particle still has some kind of a speed. The speed doesn't become zero. Okay, it's just that whatever the speed you have here is not enough to keep the string taut, because you need to have a certain speed above. I mean, you need to keep the speed above a certain figure to have it taut. But over here, when the string becomes slack, it means the speed you have here is not enough to keep it taut. So after this point onwards, the string has no part in this. Okay, because it completely becomes slack. So now the particle is on its own, and it has a certain speed here, right? So shall we find that speed? It has a certain speed here. Okay, so it has a certain speed here. Let's find that speed. Let's say this is V1. Okay, I want to find the V1 speed. So how do I get the V1 speed? That's easy. What you do is you have the tension equation. So you made tension equal to 0, and you got cos theta is minus 1 over 3, right? Okay, so remember now with the original equations we made are with respect to theta, not alpha. So because of that, if you want to find the speed at that point, you could take the velocity equation. We found a general equation for the speed. So at the last point of the circular path, so this is the place where the particle leaves the circular motion, right? After this point, the particle doesn't perform circular motion anymore. But at the very last point, okay, the theta value, at the very last point where the particle is going to leave the circular motion, the theta value is minus 1 over 3. Right? So take that theta value minus 1 over 3, cos theta value minus 1 over 3, and replace it here and get the speed. So what was the equation? V square equals GL plus 2GL cos theta. Okay, so GL plus 2GL cos theta. GL plus 2GL cos theta is minus 1 over 3. So V square equal, taking the common denominator, 3GL minus 2GL over 3. So V square equals GL over 3. V1. Okay, so I'm getting a specific speed now. Okay, at the V1 means when theta is minus, cos theta is minus 1 over 3, the place where you are leaving the circular motion. So V1 is root GL over 3 meters per second. So guys, this is the speed that the particle starts leaving the circular motion. And with this particular speed, the particle now starts what? With this particular speed, the particle now starts to move with the projectile motion. All right. Okay. So then in the projectile motion also, it's not gonna it's going to kind of go in kind of a path like this. Can you guys see? So some kind of a path like this. Can you guys see what's going on here? So guys, this is important. As you can see, now it doesn't stick to the circular path, but it goes in this projectile path. Okay, it goes in this projectile path. So it goes in a path like this. Okay, so some path it goes with it starts like this and comes down. So they are asking you to find the maximum height above it. So guys, at this point, when you're leaving the circular path, you found the height, right? We found the total height. But from that particular height also, you can see after that height level also, it goes because of the projectile motion, it still goes to another certain small height upward. Can you see? So you have to find this height. Let me mark it as x. So you have to find this height x and add it to the previous height. Are you with me? You have to find the height the small height it achieves while performing the projectile motion and add it to the total height. I hope you guys are getting what I'm saying. So let's consider the projectile motion now. So guys, considering the projectile motion, okay, so how does M2 projectiles work? So to get the maximum height, so you can apply the, either you can apply conservation of energy. That's one way to go, or you can apply the motion equation. V equal U plus AT is equal UT plus half AT squared. So you can go with that. So first of all, let's make use of the angle here. So this is alpha. Guys, I hope you guys can see this is a 90 here. This angle over here, this is 90 minus alpha, right? This angle over here is 90 minus alpha, which means the angle, this angle here is alpha. Guys, can you see that? This angle here is alpha. Okay. All right. So I want to find the height at the maximum. I want to find the maximum height. So you guys know the rule at the maximum height. You guys know the rule at the maximum height. The y component is 0, right? The y component of velocity is 0. The x component velocity, in projectiles, the x component of the velocity does not change throughout the entire projectile motion. The x component doesn't change. So I think you can see the x component of the velocity throughout the entire journey can be found from the original one, from the beginning. So this is v1 cos alpha. Can you guys see that doesn't change throughout the entire motion? Is that clear? Throughout the entire projectile motion, the horizontal part of the thing doesn't change. Okay, so either you can, so I'm going to go, actually you can go with any one of the two approaches. Now, I think maybe using conservation of energy from here to here is easiest. Okay, so it's fine. You can go with any method you prefer. So if I go with conservation of energy, okay, so if I go with conservation of energy, okay, so then I'll be using conservation of energy from the lowest point here to the highest point, okay. So I will use the GP 0 level. Now in question to question, you can arbitrarily decide the GP 0 level to make things easier for you, okay. So for this projectile motion, I'll set the GP 0 level here to make things easier for me. So why do I need to make it more complicated? Right? Because it's easy to get the X value directly when I set the GP 0 level here, right? Guys, so you can set that arbitrarily. So at the beginning, the speed. What's the speed at the beginning? So you're talking about speed, okay? When you're doing conservation of energy, you are not talking about components of speed, not about horizontal or vertical components. You're talking about the speed. Like it doesn't have the direction, doesn't matter here. So we have the speed v1. So at the beginning, you have kinetic energy, right? So kinetic energy is what you have. You are at the GP 0 level, so you don't have a potential energy. At the very top point, guys, at the very top point, this is a place where you have to be cautious when you're using conservation of energy. You definitely have GPE, because you have reached a height X above, vertical height X above the GP 0 level. But what about kinetic energy? So many people do the mistake of thinking at the highest point, kinetic energy is 0. Is it 0? That's a mistake that everyone does. At the highest point, is the kinetic energy 0? It is not 0. So I was just now telling you, throughout the entire motion, the vertical, the horizontal component of velocity stays. So at the very top, even though the vertical component is 0, the horizontal component is there. Okay, the horizontal component is there. Therefore, the resultant speed here is given by Vx. Because when we are getting the speed, we take both the horizontal and vertical components into account and get the resultant, right? So at the very top, the resultant speed is Vx, because Vy is 0. The only speed you have is the x component. So basically, you have kinetic energy final also given by the horizontal x components. There is a speed at the top. Okay, just there is a speed. So for speed, it doesn't look into the direction, right? Speed means just the magnitude. So if you take the magnitude of the speed at the top, Vx square plus Vy square root, you get this Vx answer because Vy is 0. I hope you guys can understand that, right? At the very top, normally to get the speed, you square and root you sum the squares and root for the two components. So Vx square is there, Vy is 0. So which gives you Vx as the speed. All right. Okay, so kinetic energy initial half mv1 square. So over here, we don't need to resolve because we already have the speed. Okay. GPE mg h is x because I have used this height as x. Kinetic energy half m v square. So v square is the x component, v1 cos alpha square. Can you guys see? v1 cos alpha square because that's the speed at the top. All right, so we can cancel out m here. Everyone has the mass m. You can multiply the equation with 2, v1 square, 2gx. When you multiply with 2, you only have this is v1 square cos square alpha. Can you see? Okay. So we just found the v1 square value, if I'm correct, right? We found the v1 square value as gl over 3. Can you see? We found the v1 square value as gl over 3. So let's put that value. So this is gl over 3 equal to gx plus this is v1 square is gl over 3. What about cos alpha? I think we found cos alpha, right? Cos alpha was 1 over 3. Can you see? Cos alpha is 1 over 3. So it's a square. So gl over 3 2gx. This is going to be gl over 3 3 square. That's 9. So that's 27. So gl over 3 minus gl over 27 equals 2gx. Actually, g is common to everyone. I should have cut it out. Okay, so L over 3 minus L over 27, how much is that? 3 times 9. So 9 minus 1, 8 L over 27. Is that correct? 8 L over 27 equals 2x. So the G cancels out. Right? The 2 is there over here. Okay, so then you get your x equals, when we divide by 2, 4L over 27. 4L over 27. Can you guys see? So the x distance is 4L over 27. So what's the total height reached above it? So total height reached above A is how much? The total height you reach above A is the L plus the L cos alpha plus the x. Can you see? So it's L plus L cos alpha plus the x. I think L plus L cos alpha value we found it previously, right? L plus L cos alpha value we found previously as 4L over 3 in the previous part. X value is 4L over 27. So add them up. Add them up. 4L over 3 plus 4L over 27. That's 40L over 27, right? Yeah, that's 40L over 27. This is the total height that you reach above the point A. This is the answer for part C. So guys, I hope you understood this properly, right? So this is a full vertical circular motion sum. So it's not just limited to the law of conservation of energy and it's equal ma towards the center, but you are also required to know what happens after the particle leaves the circular motion. Okay, so basically after the particle leaves the circular motion, the particle starts moving in a projectile motion and they ask you questions regarding the projectile motion as well. So that requires you to know M2 projectile. So if you are good with M2 projectiles, you can either do this projectile motion by using conservation of energy, or you are also okay to go with motion equation. V equal U plus AT, V square equal U square plus 2A should work here. But if you're working with motion equations, then you need to take components. Like you can't work with V1 here. You have to take the V1 cos alpha, V1 sin alpha. So you have to work with components. Okay. So if you want, I can also show you how to get it with components. Okay, just to quickly. Okay, using components of speed. Okay, let me show you how to get that also, so that there's no confusion. So you can do it in either of the ways. So if you use components of speed to get the same answer, So this is V1. Okay. What you do is you need to resolve that you can see. This is going to be V1 sine alpha. Okay, this is going to be V1 sine alpha, the other side V1 cos alpha. All right, so you could use here V square equal U square plus 2as upward. So V is the final speed. So final speed, now remember when you're using components of speed, you are working with horizontal vertical. So when you're at the very top point, the vertical component of speed is 0. Okay, so this is not working with energy. Okay, we are not working with energy. Now we are working with component. So when you're working with the vertical component, the V is the final speed at the top point, that's 0. U is the initial speed, the vertical component where you started the projectile motion, that's V1 sine alpha. Yeah, I'm showing you how to get the same answer in the different method now. Okay, so V1 sine alpha plus 2 into acceleration. You know your projectile motion moving upward, therefore it's negative. You have used this equation upward. So G is negative and S is the x distance. Can you guys see? So 0 equals V1 square sine square alpha minus 2gx. Take minus 2gx here plus 2gx. V1 square was GL over 3, right? Am I correct? V1 square was GL over 3, right? Yeah, I think our V1 square was GL over 3. Yeah. So GL over 3 sine square alpha, guys. So you can give, if you want now cos alpha, we have found as 1 over 3. Either you could draw the triangle and get sine alpha. So cos alpha is 1 over 3. Cos is adjacent over hypotenuse. Then you can use Pythagoras theorem. 3 square minus 1, that's root 8. Or you could even get sine square by using 1 minus cos square. So you need to be good with your P2 trigonometry. Okay, sine square is 1 minus cos square, P2, P3 trigonometry. So sine square alpha opposite over hypotenuse, that's root 8 over 3 whole thing square. So 2gx equals gl over 3 into 8 over 9. So guys, g cancels and you can see x becomes 4l over 27. Can you see we get the exact same answer for x regardless of which method we use? So I think you can see, I think components of speed was shorter, right? Okay, it doesn't matter. So any of these are fine. So you can see using conservation of energy also I get the x value 4l over 27. Using components of speed also I get the x value 4l over 27. You can use any of these methods. But anyway, the final answer is not 4l over 27. You have to add that value to the previous height it achieved and then give the total height above A. All right. So I hope this is clear. This is a complete sum in vertical circular motion.